Hi, my name is Michael Pendazis, and this is the review video for Math 231 for test number 3. Okay, so let's go over the review problems on the review sheet for test number 3. It looks like this. So let's start with the chapter 5 review problems. Okay, so this is chapter 5. And so let's start at 5.1, number 9. So 5.1, number 9, for number 9, it gives you this matrix. 6, 3, negative 8, 0, negative 2, 0, 1, 0, negative 3. So here's the matrix, and so look at your book please during this video. And so in 9 it says find the characteristic equation, the eigenvalues and bases for the eigenspaces of the matrix, okay? So we want to first find the characteristic equation. So the solutions of for the eigenvalues of that matrix A is all the solutions lambda to the equation determinant of lambda I minus A is equal to 0. So the determinant of lambda I minus A is lambda minus 6, negative 3, 8, 0, lambda plus 2, 0, negative 1, 0, lambda plus 3. That's the determinant of lambda I minus A. Let me just make sure. Good. Okay, so that's the term lambda I minus A, and you set that equal to 0, so you find all the values of lambda that satisfy that equation. And so to do that, let's find the determinant of that matrix. And so let's take the cofactor expansion along the second row of that matrix to find the determinant of that matrix. And so that determinant is lambda plus 2 times the determinant of the corresponding submatrix, which is the determinant of that, minus just that, and that's equal to 0. And so now the determinant of that is this times this minus that times that. So this is lambda plus 2 times lambda minus 6 times lambda plus 3 minus 8 times eigen 1, which is negative 8, and so this is going to be plus 8. That's equal to 0. So this is lambda plus 2 times lambda squared minus 3 lambda minus 18 plus 8 is equal to 0. Okay, and so lambda plus 2 is equal to lambda squared minus 3 lambda minus 10 is equal to 0. And so this is lambda plus 2 times lambda minus 5 times lambda plus 2 is equal to 0. Okay? So now the characteristic equation is lambda plus 2 times lambda minus 5 times lambda plus 2 is equal to 0. And so the eigenvalues of A are, I want to use a marker here. The eigenvalues of A then are the values of lambda that satisfy that equation, which is negative 2 and 5. So those are the two eigenvalues of that matrix. Those are the two values of lambda that make one of those factors 0, negative 2 and 5. So those are the so the characteristic equation, we can call this the characteristic equation, right? The product of those two things is 0. That's the characteristic equation. Those are the eigenvalues. And the bases for the eigenspaces of the matrix. And so we're going to find the bases of the eigenspaces of the matrix. And so we need to find the eigenspaces corresponding to each of those eigenvalues. So for lambda equals negative 2, that would be the general solution to, you plug in negative 2 here, and you get negative 8, negative 3, 8, 0, 0, 0, negative 1, 0, 1. 0, 0, 0 here. And so we're going to find the general solution. We're finding a general solution, right, to lambda I minus A times x is equal to 0. We're finding the general solution to that. That's the eigenspace corresponding to lambda equals negative 2. And so we're going to find it using its corresponding augmented matrix here. And so we're going to get this to reduced echelon form. And so to do that, let's put the third row, the negative 1 times the third row, move to the first one. And this one I'm going to put in the second row, but I'm going to take negative 8 times this row and add to that one, so that's going to become a 0. This is going to become, it's going to stay negative 3, and then this is going to be a 0 and 0. and then the third row is just all zeros, and that's going to stay all zeros here. And so now, multiplying this row by negative 1/3, I get 0, 1, 0, 0. This is 1, 0, negative 1, 0. And those are all zeros. And so now, that means that the eigenspace corresponding to lambda equals negative 2, if these are leading ones, so the leading coefficients would be the first two variables, and the third variable would be a free variable. And so I'm going to let x3 equal to t, then x2 is equal to 0, and x1 is equal to t. And so the eigenspace corresponding to lambda equals negative 2 are the solutions x1, x2, x3 that equals t, 0, t, which equals to t times 1, 0, 1. And so it's asking to find bases for the eigenspaces of the matrix. And so one basis, the basis for the first eigenspace corresponding to lambda equals negative 2, the basis would be just the set containing one vector, 1, 0, 1. That would be one basis for the eigenspace corresponding to lambda equals negative 2. And so that's the basis of the eigenspace corresponding to lambda equals negative 2. Set containing just one vector, 1, 0, 1. It spans the vector space and it's linearly independent as a single vector that's non-zero. Okay, so we found the basis for the eigenspace corresponding to lambda equals negative 2. Now let's find the basis corresponding to lambda equals 5. 5 says negative 1, negative 3, 8, 0, 7, 0, negative 1, 0, 8. Okay, and so I just plugged in lambda equals 5 here, and then everything else stay the same. And so now I'm gonna take I move this to the first row, but make it negative 1 times it. So 1, 0, negative 8, 0. I'm going to multiply this by 1/7, and so you get 1, 0, 1, 0, 0 there, 0, 1, 0, 0 there. And then this row, which I haven't dealt with, I'm going to take this and add it to that. And we're going to get 0, negative 3, 0, negative 3, 0, 0. And so then that will, 3 times this row add to that one, I'll just get all zeros in the third row. And then this, I'll get 1, 0, negative 8, 0. And so that means that these two are leading ones. And so x3 is the free parameter. We can't hold the marker. x3 is t, and so x2 is 0 again. But now x1 is equal to 8t. So that means that the solutions x1, x2, x3 is equal to 8t, 0, t, which is t times 8, 0, 1. And so the basis for the second space is the set one vector can 8, 0, 1. There. And so that basis is a basis for the eigenspace corresponding to lambda equals 5. It's now had bases for each the eigenspaces correspond to each eigenvalue of A. And that's 5.1, number 9. Okay? Let's keep going. So find a matrix, okay, so 5.2 number 7 control, let's look at number 7. Find a matrix P that diagonalizes A and check your work by computing P inverse AP. So here A is equal to the matrix 2, 0, negative 2, 0, 3, 0, 0, 0, 3. So find a matrix P that diagonalizes that matrix A. Okay, and then check your work. Okay, so to find a matrix P that diagonalizes A, we have to first find we have to first find all the eigenvalues of A. So let's do that. So the determinant of lambda I minus A is equal to 0. And so the determinant of lambda I minus A is lambda minus 2, 0, 2, 0, lambda minus 3, 0, 0, 0, lambda minus 3. Determinant of that is equal to 0. And so now the determinant of an upper triangular matrix is just the product of its diagonal entries. And so the determinant of that upper triangular matrix is lambda minus 2 times lambda minus 3 times lambda minus 3 is equal to 0. So the eigenvalues of lambda equals 2 and 3. Those are the eigenvalues of A. Okay, and so now we're going to find the eigenspaces corresponding to both lambda equals 2 and lambda equals 3. So the eigenspace corresponding to lambda equals 2 is the general solution of lambda I minus a times x is equal to 0. So finding the general solution of that equation is finding the eigenspace corresponding to lambda equals 2. So lambda I minus a is this matrix, and so but we're going to plug in lambda equals 2 into that. So it's going to be to 0, 0, 2, 0, negative 1, 0, 0, 0, negative 1. And so then there you go. So then now that's the augmented matrix corresponding to that linear system. And so now we're going to get this to reduced echelon form. And so I'm just going to move this to switch these two rows and get this 0, 0, 1, 0. And now if I take negative 2 times this and add to that, I'm going to get all zeros here. And then negative 1 times this, I'm going to get that. So actually, no. So actually, I'm going to multiply this by negative 1 and make that a 1. And I'm going to say negative 2 times, I'm going to just add 2 times this to that. And, wait. Oh, okay. So, alright. So this is what should happen. This should be a 0, 1, 0, 0, 0, 1, 0, 0, 0. It should be like that. Okay. I move this to the first row, multiply it by negative 1. This becomes a 0 row. That becomes 1. Okay, so we get that. And so this is just that augmented matrix in reduced echelon form. And so now x2 and x3 are leading ones, and so those are leading variables. So x1 is the free variable. So if I let x1 equal to t, x2 is equal to 0 and x3 is equal to 0. So that means the solution x1, x2, x3 is going to equal t, 0, 0. And so that's going to be t times 1, 0, 0. And so the basis corresponding to lambda, the eigenspace corresponding to lambda equals 2, that basis is going to be just the basis containing one vector 1, 0, 0. It's linearly independent and expands the eigenspace corresponding to lambda equals 2, and so it's a basis for the eigenspace, that vector space. Okay, so that's our first basis. Okay, now for lambda equals 3, we're going to find all the solutions to lambda I minus a times x is equal to 0. And so the general solutions to that linear system is the eigenspace corresponding to lambda equals 3. And so lambda I minus a, when lambda equals 3, you just plug in 3 into that, and you get 1, 0, 2, 0, 0, 0, 0, 0, 0. And then you get that to reduced echelon form, but it already is in reduced echelon form. And so then you take the leading one there. So x1 is a leading variable, and x2 and x3 are free variables. So I'm going to let x2 equal to t and x3 equal to s. Then x1 is equal to negative 2s. And so that means that x1, x2, x3 is going to equal to the vector negative 2s, comma t, comma s, which is s times negative 2, 0, 1, plus t times 0, 1, 0. And so now those two vectors form a basis. Those two vectors form a basis for the eigenspace corresponding to lambda equals 3. So that basis we're going to call B2. It just contains the vectors negative 1, 0, 2 and 0, 1, 0. And so that's the basis corresponding to lambda equals 3. And so now we have a basis for both eigenspaces. This is a basis for the eigenspace corresponding to lambda equals 2, and this is a basis for the eigenspace corresponding to lambda equals 3. Okay? So we have that. And again, the goal is to find a matrix P that diagonalizes A and check your work by computing P inverse AP. Okay? So okay, good. Okay, just checking. So now, okay, so what we have now are a total of 3 basis vectors, right? We have 1 here and 2 here. So we have a total of 3 basis vectors between all the eigenspaces for our eigenvalues. And so we have a total of 3 basis vectors, and we have a 3 by 3 matrix. And so that means that we have enough basis vectors in order to conclude that A is diagonalizable. So if we have exactly 3, which we do, A is diagonalizable. But if we have less than 3 total basis vectors, then since A is 3 by 3, it would not be diagonalizable. So we have enough for it to be diagonalizable. And so now the matrix P that diagonalizes A is going to be a matrix consisting of columns that are the basis vectors in those. I'm just going to choose any order I want. So I'm going to choose this to be the first column. I'm going to choose this basis vector to be the second column, and this basis vector to be the third column. So that P diagonalizes A, and P inverse AP is going to equal the diagonal matrix whose diagonal entries are the corresponding eigenvalues of the rows we chose here. So this first column, so this first column was B1, and B1 corresponded to lambda equals 2, and this was corresponding to lambda equals 3. So since that corresponds to lambda equals 2, that goes there. The second and third rows were in the eigenspace corresponding to lambda equals 3, and so those eigenvalues there will go there. So this is the matrix P that diagonalizes A, and P inverse AP is equal to that diagonal matrix for that P. And so we computed P inverse AP there. And so that is number 7 in 5.2. So let's keep going. So let's go to 5.3 and do problem number 2. Okay. Okay, so 5.3, number 2. Okay, so 5.3, number 2. So 5.3, number 2, it says find U bar, the real view, imaginary view, and the norm view. And so for number 2, U is just equal to the vector 5.3, number 2. Yeah, okay. U is equal to 6, comma 1 plus 4i, comma 6 minus 2i. That's U. Okay, and so now we're going to find U bar. So U bar is just the complex conjugate of each component of U. And so that's the complex conjugate of each component put in the respective components of U bar. So we found U bar there. Now the real part of U, just the components of U, real part of U are just the real components of those. And so you get 616. The imaginary component of U is equal to the imaginary component that has 0, the imaginary component that has 4, the imaginary component that has -2. So that's the imaginary component of vector U. That's the imaginary part of vector U. And then if we want to find the norm of U, we're going to find the norm of U relative to the Euclidean inner product. And so that's going to be the square root of 6 squared plus 1 plus 4i squared plus 6 minus 2i squared. Okay? And so when we find that, that's the square root of 36 plus, when you take 1 plus 4 and you square it, you're going to get 1 plus 8i minus 16. Okay? And then 6 minus 2i squared, you get 36 minus 24i plus minus 4. Okay, and so when you add all that up, you get 36 plus 1 minus 16. That's 36, 37, 21, 57 minus 4 is 53. And then 8i minus 24i is minus 16i. And so that is the norm of U. Okay, so it's 1 plus 8i minus 16, 36 minus 24i minus 4. That's good. 21, 57, 53. Good. That's it. Okay, so now that's all of 4 things for 5.3, number 2. Okay, so now 6.1, numbers 1 to 10 and 12 are the problems in this section. Okay, so 6.1, numbers 1, 10, and 12. So let's look at number 10. So for number 10, U is equal to 1, 2, negative 3, 5. And V is equal to 4, 6, 0, 8. Okay, so we're going to compute the standard inner product of M sub 2 to the given matrix. So we'll compute the standard inner product of U and V, but that's just the product of the sum of the products of the corresponding entries of U and V. So that's just 1 times 4 plus 2 times 6 plus negative 3 times 0 plus 5 times 8. So that's equal to 4 plus 12 plus 0 plus 40. And so that's equal to 56. Okay, so that's number 10. And so let's keep going. So 6.2. So 6.2 is numbers 2, 13, 19. So 6.2, number 2, 13, and 19. Let's do number 19. Okay, so for number 19, let P sub 2 have the evaluation inner product at the points x naught equals negative 2. X1 is equal to 0, and x2 is equal to 2. And so we want to show that the vectors P equals x and Q equals x squared are orthogonal with respect to this inner product. With respect to that inner product, the evaluation inner product at those points. And so the inner product of P and Q, according to the evaluation inner product, is P of x naught times Q of x naught plus P of x1 times Q of x1 plus P of x2 times Q of x2. Okay? So that's the evaluation inner product of P and Q at x naught, x1, x2. Okay, so we're going to see whether we want to show that P and Q are orthogonal. We want to show that the inner product, that this value is 0. So P of x naught is P of negative 2. Q of x naught is Q of negative 2 plus P of x1, which is P of 0, times Q of x1, which is Q of 0, plus P of x2, which is P of 2, times Q of x2, which is Q of 2. So P of negative 2 is negative 2, because P of x is x, and Q of negative 2 is negative 2 squared, which is 4. And so plus P of 0, which is 0, Q of 0, which is 0, plus P of 2, which is 2, times Q of 2, which is 4. And so this is equal to negative 8 plus 0 plus 8, which is equal to 0. So the inner product of P and Q, according to the evaluation inner product at x naught, x1, x2, is 0. And so that implies that P and Q are orthogonal. Okay, so P and Q are orthogonal. So that's number 19 in 6.2. So let's keep going. So I'm going to do 6.3. Okay, so 6.3, number 7 and 11. All right, so 7 and 11. Okay, so let's do number 7. So number 7 says in 6.3, verify that the vector is v1, which is equal to negative 3/5, 4/5, comma 0. And v2 is equal to 4/5, 3/5, 0. v3 is equal to okay, so you want to verify that those three vectors form an orthonormal basis for R3 with respect to Euclidean inner product. So, okay, so in order to be an orthonormal basis for R3 with respect to Euclidean inner product, we need to show that they are linear. So we need to show that the norms of each of those vectors is 1. So the norm of v1 is the square root of negative 3/5 squared plus 4/5 squared plus 0 squared. And then so that's the square root of 9 over 25 plus 16 over 25 plus plus 0. That's equal to the square root of 25 over 25, which is the square root of 1, which is 1. So the norm of V1 is 1. The norm of V2 is equal to the square root of the sum of the squares of the components of V2, which is 4/5 squared plus 3/5 squared plus 0 squared. That's equal to the square root of 16 over 25 plus 9 over 25 plus 0, which is equal to the square root of 25 over 25, which is the square root of 1, which is 1. So the norm of V2 is also 1. And then the norm of V3 is the square root of the sum of the squares of its components, which is 0 squared plus 0 squared plus 1 squared, which is the square root of 1, which is 1. And so the norm of V1, V2, and V3 are all 1, and so they're all unit vectors. Okay? So that's V1, V2, and V3. Now, okay, so the norms of all those vectors is 1. And so in order to form an orthonormal basis for R3, so first off, there are 3 vectors, and we want to show 3 vectors form a basis for R3. And so we know that we don't have to show both linearly independence and spanning of R3 because we have the same number of vectors as the dimension of the space R3. So we only need to show one thing or the other. We only need to show it linearly, that set's linearly independent, V1, V2, V3, or that it spans all of R3. And so I think I'm gonna let's prove it's linearly independent. Let's prove V1, V2, V3. Let's prove that set is linearly independent. Because then, once it's linearly independent, since there's 3 vectors that are linearly independent in a vector space of dimension 3, that means it's a basis. Okay? And so I chose this one because it's going to be easier, because V3 is not in the span of V1 and V2, because V3 has a 1 in the third component, and neither V1 nor V2 they're both 0 in the third component. So V3 is not in the span of the set V1 and V2. And so that means that if the set V1, V2 is linearly independent, which it is, if this set is linearly independent, then we can add the vector V3 to that set and it'll stay linearly independent. Okay, so this set is linearly independent because it's a set containing 2 non-zero vectors and neither is a scalar multiple of the other. If you look at this one, in order to multiply this to get, you'd have to multiply this by negative, negative 4/3. This times negative 4/3 will give you that. But if you multiply this by negative 4/3, you won't get 3/5. So these are 2 non-zero vectors that neither is a scalar multiple of the other. And so the set V1, V2 is linearly independent. But now we have a set V1, V2 that's linearly independent and a vector V3 that's not in the span of any of the vectors in that set. And so that means we can add the vector V3 to that set by the plus minus theorem, and we'll still have a set that's linearly independent. So that means the set V1, V2, V3 is linearly independent, and since it's a set of 3 vectors in a space of dimension 3 that's linearly independent, it's also a basis. And so now I just showed in words, saying out loud, that set is a basis for R3. And because it consists of only vectors of length 1, it's an orthonormal basis. It's not just a basis, it's also a basis for all, not yet orthonormal basis. It's a basis where all the vectors are of length 1. We also have to show it's an orthogonal set. Okay? And so we have that it's a basis. We have that it consists of only unit vectors. But in order to be an orthonormal basis for R3, we need, in addition to that, we need to show it's an orthogonal set. That if you take any 2 vectors, their inner product is 0. But if I take the inner product of this with this, it's obviously 0, because this times this is 0, that times that is 0, and that times that is 0. So the inner product of V2 and V3 is 0. The inner product of V1 and V3 is also 0. And if you take the inner product of V1 and V2, you're going to get negative 12 over 25 plus 12 over 25, which is 0. So the inner product of any 2 of the 3 of these vectors is 0 in any order you want to choose. Okay? And so it's also an orthogonal set. And so the set V1, V2, V3 is a basis consisting of only unit vectors, and it's an orthogonal set. And so that means that it is an orthonormal basis for R3. Okay, so that set is an orthonormal basis for R3. Okay, and so we could express the vector U as a linear combination of V1, V2, and V3. Alright, okay, so this is U, and it's the vector 1, comma, negative 2, comma 2. And so we're going to express this as a linear combination of V1, V2, and V3. So it's C1 times V1 This one isn't that bad, so then let's just, won't require that much pencil pushing. So we could just go ahead and just do this really quickly. Okay, so the reason why this is going to be fast is because this third component is a 2. Neither of these two vectors have a third component. That means in order to get a 2 here, C3 is going to have to be a 2. That gives you one of the 3 constants right off the bat. So this is going to be a 2. And we won't have to worry about this one. So now we just have to define C1 and C2. Well, I guess this is a little bit of work. So then, so basically, negative 3/5 C1 plus 4/5 C2 is going to equal 1. And 4/5 C1 plus 3/5 C2 is going to equal negative 2. Okay? And so, if we add 2 times this equation to that one, we're going to get a 0 on the right side. And so we're going to get negative 6/5 was 4/5. Negative 6 with 4/5 was negative 2/5 C1. And then 8/5 plus 3/5, which is 11/5. C2 is equal to 0. And so what that means is that if I move this to the other side, if I multiply both sides by 5, and I'm going to get 11C2 is equal to 2C1. So I'm going to get 11 half C2 is equal to C1. And so if I plug that in here, it's going to be a little annoying. It's going to get negative 33 over 10 C1 plus 11, negative 33 over 2 C2. I'm just plugging this in for this. So I'm getting negative 33 over 10 C2 plus common denominator 8 over 10 C2 is equal to 1. And so since that's equal to 1, we're getting negative 25 over 10 C2 is equal to 1. So that means C2 is equal to negative 10 over 25, which is negative 40 over 100, which is the same as negative 0.4. Well, negative 4/10, negative 2/5. Okay, so C2 is negative 2/5. And so since C2 is negative 2/5, you can multiply that by 11 over 2 and get C1. And so we're going to get negative 11/5 is C1. So C1 is a negative 11/5. C2 is negative 2/5, and C3 is 2. So this is going to be a negative 11/5. C2 is going to be negative 2/5, and C3 is 2. And so just checking, I'm going to get 33/5. 33 plus 8 is... negative 3/5 C1 plus 4/5 C2 is equal to 1. 4/5 C1 plus 3/5 C2 is equal to negative 2. Negative 2/5. 11/5 is equal to 0. So that means it's C1 is equal to that. But then negative 33 over 10 C2 plus 8/10 C2 is negative 25 over 10 C2 is equal to 1. That means C2 is negative 10 over 25, which is negative 40 over 100, which is negative 2/5. If C2 is negative 2/5, then C1 is 11/5. Negative 11/5. Oh, it's fine. It is right. Okay. It is right. There's nothing wrong with this answer. It's 33 over 25 minus 8 over 25 is 25, which is 1. That's absolutely right. And then negative 44 plus 6. Negative 44 minus 6, negative 50 over 25, negative 2. Good, it works. So U is equal to negative 11 fifths V1 minus 2 fifths V2 plus 2 V3. And that's it. Okay, so that's the answer number 7. So there's nothing wrong with that answer. Absolutely right. Okay, so that's 7. And so now going to 7.1. Okay, so okay, so 7.1 numbers 4 and 15. So now, well, let's do number 4. So determine whether the matrix is orthogonal, and if so, find its inverse. So for 4a, this is the matrix. 1 half, 1 half, 1 half, 1 6, 1 6, negative 5 6, 1 6, 1 6, 1 6, negative 5 6, negative 5 6, 1 6. Oh, so I'm just going to do part A because there's also part B. So here's the matrix, and we have to determine whether the matrix is orthogonal, and if so, find its inverse. Okay, so an orthogonal matrix is a matrix is A transpose equals A inverse. But we could also think about the fact that that if the row vectors of this matrix form an orthonormal set in R4, or the column vectors of A form an orthonormal set in R4 with the Euclidean product, then it's orthogonal. So this is by theorem 7.1.1. And so this is a much better route to go to show that this is orthogonal than showing that A transpose equals A inverse. Because then if we did that, if we went this route, we'd have to find the inverse of that matrix, and that would take a lot of work. And then it would be easy after that. We could take the transpose and see whether the transpose was equal to its inverse. This would take too long, so let's not do it that way. We're going to use theorem 7.1.1 in this section to show that we can either choose rows or columns, either one, and show that the rows or columns form an orthonormal set in R4. And then that would mean that's equivalent to showing that this matrix is orthogonal. Okay, so let's choose the rows, because we usually find looking at rows easier than looking at columns. So let's look at the rows of this matrix, and then let's determine whether or not it forms an orthonormal set in R4. So in order to be an orthonormal set in R4, it's going to have to, there's 4 vectors. So we don't, in order to show it's a basis, oh no, sorry, we just need to show they're all length 1. Let's do that first. So I'm going to call this R1, R2, R3, and R4. And so let's take the norm of each row. So the norm of that is the square root of the sum of the squares. It's 1/4 plus 1/4 plus 1. That's the sum of the squares of its components, right? 1/2 squared plus 1/2 squared plus 1/2 squared plus 1/2 squared. And so that's the sum of squares. That's 4 1/4, which is square root of 1, which is 1. So the norm of R1 is 1. The norm of R2, you would take the square root of the sum of the squares of that, but you would get 1/4. 1/2 squared is 1/4. Negative 5 squared is 25 over 36, and 1/6 squared is 1 over 36, and 1/6 squared is 1 over 36. So that's the sum of the squares of the components of R2. And take the square root of that, and so this would be 9 over 36 plus 25 over 36. That's 36 there. Plus 1 over 36 plus 1 over 36. And so if you add them up, you're going to get 36 over 36. The square root of 36 over 36 square root of 1, which is 1. So the norm of R2 is 1. If you take the norm of R3, you're going to get the square root of the sum of the squares of the third row. And if you get that's 1/4 plus 1 over 36 plus 1 over 33. It's these same terms, but just in a different order. And so you can easily show that the norm of R3 is equal to 1. Then if you take the norm of R4, just like before, you're going to get the sum of squares where it's just in a different order. And so the norm of R4 is also 1. And so each row has norm 1. Okay? If you take the inner product of R1 and R2, you're just going to take, this times this plus this times this plus this times this plus that times that. You're going to get 1/4. It's going to be 1/4 plus 1/4 minus 5/16. Minus 5/12. Plus 1/12 plus 1/12. And so if you add those up, you're going to get 3/12 minus 5/12 plus 1/12 plus 1/12, and that's equal to 0. So the inner product of R1 and R2 with respect to the Euclidean inner product is 0. Now the inner product of R1 and R3 with respect to the Euclidean inner product is these multiplied by the corresponding ones of these, and you add up the sums. That's 1/4 plus 1/12 plus 1/12 minus 5/12. And so you're going to get that that's 0 also. If you take the inner product of R1 and R4, you're going to get 1/4 plus 1/12 minus 5/12 plus 1/12, and it's just these terms in a different order, and you're also going to get 0. So then if you take the inner product of R2 and R3, you'll similarly get 1/12 minus 5/12 plus, plus 1 over 36 minus 5 over 36. So if you multiply that, you get 1/4 minus 5 over 36 plus 1 over 36 plus minus 5 over 36. Okay, and that's equal to 0. And then your product of R2 and R4, then you just get 0. It's 1/4 minus 5 over 36 minus 5 over 36 plus 1 over 36, and that's going to be 0. And so, 7.1, 4, okay. It's 1/4, 4/12, 5/12. Okay, good. Just checking. 1/4, 9 over 36 minus 5. 4 over 36. 1 over 36, 1 over 36, 0. Good. Okay, and so then the inner product of R3 and R4 is just, you get 1/4 plus 1 over 36. That's 10 over 36, 5 over 36. Good, that's 0 also. Okay, and so so the inner product of R1, R2, R1, R3, R1, R4, R2, R3, R2, R4, R3, R4 are all 0. So if you take any two rows and you find their inner product, it's 0. And so that means the rows form an orthogonal set. So the rows of A form an orthogonal set, and the norm of each row vector is 1. And so that means that the rows of A form an orthonormal set. An orthonormal form an orthonormal set in R4. And so that means that this matrix is orthogonal by theorem 7.1.1. Okay? And so let's just keep going. I don't want to find the numbers. Okay, so then let's go to 7.2. Okay, so 7.2, numbers 9 and 17. Okay, so 7.2 numbers 9 and 17. Let's do number Okay, so let's do number 9. So for number 9, we have the matrix A is equal to -2, 0, -36, 0, -3, 0, and -36, 0, -23. Okay, so we have this matrix here. And so we want to find a matrix P that orthogonally diagonalizes A and determine P inverse AP. So let's find the eigenvalues corresponding to A. So the eigenvalues of A are the values of lambda such that determinant lambda I minus A is equal to 0. So the determinant of lambda I minus A is the determinant of this matrix. So the determinant of that matrix is equal to 0. That's our characteristic equation. Find the cofactor expansion of this matrix along the second row. And so we're going to get lambda plus 3 times the determinants of the corresponding submatrix. Lambda plus 2, 36, 36, lambda plus 23. That's equal to 0. So this times this minus that times that is the determinant of that. So lambda plus 3 times lambda plus 2 times lambda plus 23 minus 36 squared, which is 1296. So 36 squared is 1296, so that's minus 1296. So it's lambda plus 3 times this times this minus 1296 equals 0. So just to make sure, 36 times 6 is 216. 216 times 6 is 1296. Good. Okay, and then so we're going to multiply that out. Get lambda plus 3 times lambda squared plus 25 lambda plus 46 minus 1296 is equal to 0. Okay, plus 25 lambda plus 46 minus 1296. So that's minus 1250. And then equals 0. Okay, so then we're going to factor out that. So I'm going to get lambda plus 3 times, and I'm going to factor that out. And so in order to factor that out, I think, so I'm going to factor lambda squared plus 35 lambda minus 1250, and that's going to be lambda plus 50 times lambda minus 25. And that's going to equal 0. Because then 50 lambda plus negative 25 lambda is 25 lambda, and 50 times negative 25 is negative 1250. And so that's the factorization of that. So the eigenvalues to satisfy that equation, lambda equals negative 3, 25, and negative 50. So those are the 3 eigenvalues of that matrix A. Okay. Okay, so then, so I'm going to find matrix P that orthogonally diagonalizes this matrix. So, all right, we'll do it. Okay, so then, so this is lambda I minus A times x is equal to 0. And so if you find the set of all solutions of that equation, again, that's the eigenspace corresponding to the fixed lambda you plug in there. So the eigenspace corresponding to lambda equals, let's say, 25, is you plug 25 in, and you get, this is 27, 0, 36, 0, 28, 0. Okay, okay, so then you have this matrix, and so let's just get this to reduced echelon form. And so multiply the first row by 1 over 27, that's 1, 0, that's 4 thirds, that's 0. Multiply that by 1 over 28, get that. Then I'm going to multiply this by negative 36 and add to that, and get 0, 0. That's 0 also. Okay? And so now we have our matrix in reduced echelon form, where x1 and x2 are leading variables, and x3 is a free variable. So x3 is going to equal to the parameter t, and x2 is going to equal 0, and x1 is going to equal negative 4 thirds t. And so the set of all solutions are x1, x2, x3, which is equal to negative 4 thirds t, comma 0, comma t, which is equal to t times negative 4 thirds, comma 0, comma 1. Okay, so that is the eigenspace corresponding to lambda equals 25, and so a basis for that eigenspace I'm going to call this B1, the first basis, which is negative 4/3, 0, 1. So that's the basis of the eigenspace corresponding to lambda equals 25. Okay, and then, so let's find the eigenspace corresponding to the next eigenvalue. I'll put the bases over here. So for lambda equals negative 250, okay, you get the eigenspace of negative 48, 0, 36, 0, well, just go here, 0, 36, 0, negative 27. Okay, I'm going to get this to reduced echelon form, and so I'm going to multiply this row by negative 1 over 48, get 1, 0, negative 3/4, 0. Okay, and then I'm going to multiply this row, that's a 47, there. And so I'll multiply this row by negative 1 over 47 and get 0, 1, 0, 0. And then I'm going to take negative 36 times this row and add to that one and get 0, 0. 9, 0. Okay, let me just check that. So then you get okay, so negative 36 that goes to 0. Wait, 9, negative 36. That's a 0. Okay. Okay, fixed. Okay, so that's one x2. Those are leading variables, and then that's the free variable x3 is t. So then x2 is equal to 0 and x1 is equal to 3/4 t. And so the eigenspace corresponding to lambda equals negative 50 is x1, x2, x3, which is equal to 3/4 t, comma 0, comma t, which is t times 3/4, 0, 1. Okay, and so the basis for the next eigenspace, the eigenspace corresponding to lambda negative 50, is the contain the lone vector 3/4, 0, 1. Okay, so now that's another basis of another eigenspace, and then there's one more to go. We have the basis corresponding. We need to find the eigenspace corresponding to lambda equals negative 3. Okay, and so now we plug negative 3 in there, and we get 0, 0, 0, 0, negative 3, 36, 0, 20, 0. Okay, and so then we're going to multiply the first row by negative 1 and get 1, 0, negative 36, 0. The second row I'm going to make the third row, and then I'm just going to take negative 30, so I'm going to take 36 times this row and add to that one. I'm going to get 0, 0, 36 times 36 again is 1296. And so 1296 plus 20 is 1316. And that's 0. Okay, but then I just multiply the second row by 1 over 1316, and that becomes a 1. So that doesn't really matter. And then, that calculation. And then I'm going to take 36 times this row and add to that one and get a 0 here. Okay, so in the end, I'm just going to get 1s here. So this is going to be a 1 here and a 1 there. And so x2 is my free variable, which is, I'm going to set equal to t. x1 is equal to 0, x3 is equal to 0. And so the solutions to this are x1, x2, x3, which is equal to 0, t, 0, which is t times 0, 1, 0. Okay, and so basis corresponding to the eigenspace corresponding to lambda equals negative 3 is the set containing the lone vector 0, 1, 0. Okay, and so those are the bases for each of the eigenspaces corresponding to all the eigenvalues of A. And so now that we've done that, that was lambda equals negative 3. This was for lambda equals negative 50, and this is for lambda equals 25. And I hope I got that right, which I think I did. So that was lambda equals 25 there. Okay, so then we want to find a matrix P that orthogonally diagonalizes A. So we just need to make all of these into unit vectors. And so I'm going to make B1 prime this except as a unit vector. So the norm of this is going to be 5/3. The norm of that is 5/3. So I'm going to divide that by 5/3 to make it into a unit vector, and I'm going to get -4/5, and then I'm dividing by 5/3, and so this is going to be 3/5. And if you check, this is now a unit vector. And so now B2 prime is just going to be B2, but now a length 1 vector. And so this is going to be 9/16 plus 1. That's going to be 5/4. The length of that is 5/4. I'm going to divide by 5/4, and I'm going to get the vector 3/5, 0, 4/5. Okay, and the length of that is also 1. So that works out. And now B3 prime is a unit vector of B3. Let's say, well, I'm going to make the basis, but that's already length 1. So I'm going to just keep that the same. Okay, so now those are all now bases for the eigenspaces of A, where, and they're also orthonormal bases for each of the eigenspaces. They're only one vector. It's an orthogonal set because I can't choose 2 vectors in it. So P is going to be the first column. I'm going to make this basis vector. The second column I'm going to make this basis vector, and the third column I'm going to make the third basis vector there. Right. So those are the 3 columns of A, and so that means P is going to orthogonally diagonalize A, and D, which is P inverse AP, is going to equal. This corresponded to 25, this corresponded to -50, this corresponded to -3. And so P inverse AP is going to be that diagonal matrix, right? Where the diagonal entries are 25, -50, and -3, respectively, from top left to bottom right. Okay? Okay, and so that is the answer to number 9. We now found a matrix P that orthogonally diagonalizes A, and we determined P inverse D, which is equal to P inverse AP for that matrix. So that's 7.2, number 9. And so now let's go to 8.1. So 8.1, the problems for that section of 1 numbers 1, 10, 11. And so let's do number, just text it. Okay. So for 8.1, so for number 1, we're going to determine whether or not T is a linear transformation. And so for part A, T of A is equal to A squared. And so to determine whether or not T is a linear transformation, it has to satisfy 2 properties, right? It has to satisfy T of Ka equals to K times T of A, and it has to satisfy T of A plus B is equal to T of A plus T of B. And if it satisfies both the homogeneity property and additive property, then it's a linear transformation. Okay, so let's see if that works. So T of Ka is equal to Ka squared, which is K squared A squared. K times T of A is equal to K times A squared. Okay, so K times A squared is not equal to K squared A squared for every K. Let's say K is equal to 5, and you can choose an appropriate A where that doesn't work. So Ka squared does not necessarily equal K squared A squared, and so that means that this property fails. And so T is not a linear transformation. Okay? Okay? So for B it says T of A is the trace of A. and you can show that is a linearly independent function. You could show that these two properties hold and it's a linear transformation. And if you want to find the kernel of A, well, the kernel of A, what is A? A is it's M to the 2, 2. So A is a 2 by 2 matrix. So the kernel of A would be all the matrices whose trace is 0. And so it would be all the matrices of this form, where A and B could be any number, because the trace is 0 of any matrix like that. Okay, so the kernel will just be the set of all these matrices such that A and B are real numbers. That would be the trace of A. The matrices of this form where A and B are real numbers. That means in the set of real numbers, A and B are reals. Okay? That's the trace of, not the trace, sorry, that's the kernel that's the kernel of T. The kernel of T is the set of all elements that T would map to 0. All the 2 by 2 matrices whose trace is 0. Okay? And so that is 8.1, number 1. And so now 8.2, number 4. So 8.2, number 4. When you have number 4 here, so number 4, let's go with part number A, where capital A is equal to this matrix 1, 2, 2, 7, 3, 9. So that's matrix A. And determine whether multiplication by A is 1 to 1 by computing the nullity of A and then applying theorem 8.2.1. So let's find the nullity of A. So the nullity of A is just all the solutions to AX equals 0 of that matrix. And so in order to be a solution to that equation, this matrix, right, you would have to multiply this by this and get 0, 0, because this is a 3 by 2 matrix. And this way, then this is a 2 by 1. You're going to get a 3 by 1 matrix here. Okay, so we want to find values of x1, x2 where that holds. And so, well, the set of all vectors like that would be the nullity. Would be the null space. And then the dimension of that space is the nullity. Okay. Okay, actually, there's more than one way to do this. So then you could, okay, another way you could do it is if you take this, you get to reduced echelon form. So this would be 1, 2, but then negative 2 times the first row to the second one, you get 0, 3, multiply this by 1/3, you get a 1 there. Negative 3 times this plus this, you get 0. 3, 0, and then you could get a 0 there, and then you could add negative. So you get to getting this to reduced echelon form, you get that. And so now you have 2 leading 1s there, and so that means that the rank of A is equal to 2 because there's 2 leading 1s. The rank plus the nullity is the number of columns. There are 2 columns here. N is equal to 2. So by the dimension theorem, right, the rank of A plus the nullity of A is equal to N. Dimension theorem. So N is 2. So that means that 2 plus the nullity of A is equal to 2. So that means the nullity of A is equal to 0. Okay, by the dimension theorem. And so, and then, so if the nullity of A is 0, then that means that the kernel of A was the 0 set. Why is that? Because the nullity of A is the dimension of the null space of A. The dimension of the null space of A is the dimension of the space of all vectors x that satisfy that equation. Well, if it's of dimension 0, that means it's only 1 point, and 0 satisfies that equation. So that means that the set of all solutions to that equation is just the 0 set, or the kernel of A is the 0 set. And so by theorem 8.2.1, that would imply that that multiplication by a is 1 to 1. And so the implication of that is multiplication by a is 1 to 1. Therefore, multiplication by a is 1 to 1. And that's by theorem 8.2.1. Because that's for a, and then so that explains that. 8.3, number 12, we did at the end of the last lesson. At the very end of the lesson. Okay? And so that is the review, and so keep studying.